longtime Clojurist, creator of the Enlive and Parsley libraries, and co-author of the book Clojure Programming. Please help me welcome Christophe Grand, who is here to talk to us about transducers.
So, transducers are awesome, but at the same time, they often left me in a deep despair and frustration. And I'm going to explore how I ended into this situation. So, what happened? At first, in Clojure, we had the sequences. It was a pretty simple model. In sequences, you have a console made of an item and the rest of the sequence. And it was cool because it was persistent. Results were cached. We had some strict laziness. Results were computed, values were computed at the time they were consumed, unless they were already cached. But they had a big problem. They put the garbage collector under a huge pressure. And so you had to rewrite your code to use mutation to avoid a lot of object churn and putting pressure on the garbage collector. The garbage collector is efficient at collecting short-lived objects, but no garbage is better than little garbage. So then we add chunked sequences. Chunked sequences were just like sequences, except that having a console holding only one item, the console was able to hold several items, typically 32. But it was good it was good because it reduced the allocation rate. It didn't reduce the allocation rate by 32, but by about 10, because for each chunked console, you have the chunk console itself, the buffer, and the array. So it's 3 objects to all the values. But it was still an order of magnitude less allocations than with regular cons. And plus, it had the additional benefit of better memory locality. So it was more friendly with the CPU cache. And one consequence, an intended consequence of chunked laziness is that chunked sequences is that laziness has to be relaxed. You can't have strict laziness when you want to process things in a batch fashion. And so we had to relax the laziness. And I think it wasn't a bad move, because it also prevented people from relying on laziness to implement control flow in Clojure. And this is a bad idea for Clojure, which is not a pure functional language. But a real problem of chunked sequences is that in every sequence function, you had to have 2 branches, one for regular cons and one for chunked cons. So you had some kind of code duplication, and the code for the chunked cons was a bit ugly. So very little Clojure sequence functions do support chunked sequences. So then we introduced the reducers. The reducers try to inverse the control. It's not your code which is iterating around the collection. It's the collection which is calling your code. And reducers are not that bad. We still don't, this time we have no allocation, no console, no nothing. They are mostly lazy, but they are not persistent. So you have to cache yourself the results into a persistent collection. But this time, we didn't have branching code. We had duplicated code. We have regular map in Clojure Core, and we have reducer map in the reducer namespace, and so on for filter, for mapcat, and so on. So we were starting to create different dialects. And at the same time, in CoreSync, there was the same problem. They were implementing map on top of channels, filter on top of channels. And it was leading to more and more fragmentation if you add some logic implemented in terms of map and filter and remove and so on. If you happen to use it to implement it on top of the map, filter, and so on of sequences, you can only use them on sequences. But this logic would have been as valid if it has been written on top of the reducer, map, and filter, and so on, of the channel versions. So you had to duplicate the logic to be able to express the same thing in 3 different contexts. And if you go back to the rationale of Clojure, you will find this quote by Alan Perlis, this quote says that it's better to have 100 functions operating on one data structure, or in the case of Clojure, it's more like one abstraction, than having 10 functions operating on 10 abstractions. But at this time, we were fragmenting the Clojure ecosystem by creating islands of code, one for reducers, one for sequences, one for CoreSync. And that's where transducers come in play. They still feature no allocation, like reducers. They are mostly lazy. They are still not persistent. But this time, we don't have the fragmentation problem. The transducer only expresses the transformation. And you have to put the transformation into a context to make it run. But a bit like the chunk sequences, we have the problem of the branching implementation, because if you look at the code for map in Clojure Core, you'll see the map on sequences, and right below or above, you'll see the map for transducers. So it's a bit similar to the problem we had with chunk sequences, but not quite. At first, I forgot to mention that we have this transducing context. The transducing contexts are functions that take a transducer and apply it to a stream of data. So it can be transduce, to apply it to anything which can be reduced. It can be sequence, to create a lazy sequence out of it. It can be into, to automatically create a persistent collection out of the processing. And this maps really, really well to the way I used to write my code. I never considered sequences to be an end, but only the medium of computation. So I had a source of data, perform some sequence operation on them, and at the end, I had to realize the computation, either by creating a persistent collection or writing it to disk or sending to the network, whatever. So into with the additional transducer argument maps really well to that. And then there's induction, which allows you to create a virtual collection, and from this virtual collection, you can either iterate over it using an iterator or reducer or a sequence. And in CoreSync, you can apply a transducer to a channel or to a pipeline. So it's 6 contexts by default. So back to chunked and transducers. The big difference is that in chunk transducers, the implementation in chunk sequences, excuse me, in chunk sequences, the implementation was quite complex because you had to have the implementation, the iteration on the buffer of the chunk const embedded in every implementation of a chunked sequence of function. While with transducer, we only have to care about the completion of the iteration. The iteration itself is cared by the collection, by the context. So it's easier to write a transducer than to write a chunk sequence function, and it's also more efficient. You can only write the transducer, and using sequence, you get the sequence function for free. While it wasn't possible, or rather, it would have been possible, but it wouldn't have been efficient at all to do the same thing with chunk sequences. So overall, it's a better situation than with chunk sequences. And the deep irony is that when you apply a transducer in a sequence context, you get a chunk sequence out. So everything ties together at the end. So the real takeaway is that transducers enable reuse, enable you to write some code and test it locally in the REPL in a context which is completely independent of the real context of application. And so your code is more reusable and more easily testable. So it's quite powerful. And as an added benefit, they are more efficient. But what's really a transducer? Formally, a transducer is a state machine which consumes a stream of data as internal state and outputs another stream of data. Or if you prefer, if an automaton is just a predicate on sequences for broad acceptation of sequence, not strictly speaking the Clojure sequences, a transducer is an arbitrary transformation from sequences to sequences. And a Clojure transducer is expressed as a function taking an output tape and returning a new input tape, and this input tape will be passed to the next stage, which will consider your input tape as its output tape, and everything will be chained together. And the tape happens to be a reducing function. So, OK, it's a reducing function, but what's really is in this reducing function? If we consider the simplest transducer, the identity transducer, you see that it must have three arities. So it takes the original reducing function, the output tape, and then it returns a new reducing function, the input tape. And this reducing function must have three arities. 0 argument for initialization, 1 argument for completing the computation, and 2 arguments for processing 1 input. But it's really a nest of bugs. Writing your own transducer is really not a pleasant experience. I have written a lot of transducers, and I'm not even sure that I've done it right. So the first problem is that you realize that init must only delegate to the underlying stream, the underlying reducing function, because there's no guarantee that init is going to be called. In several contexts, init is never called. But just in case you happen to use it in a context where it is called, you have to implement it. So you have to implement it, but you can't do anything in it. Boilerplate at its best. So it means that you can't touch the accumulator because you don't have a word to say. You can't modify or wrap the accumulator during the initialization, since you have no guarantee of being able to initialize in the first. And the second corollary is that you have to keep your state in a mutable box, closed over by your reducing function. Maybe you think, oh, no, I can be more clever. In the step function, I'm going to check whether my accumulator is wrapped the first time, and if not, I'm going to wrap it, and no. The sequence context is always going to give you nil as the accumulator. No matter what you return the previous time, you get nil back. So you can't put state in the accumulator. Don't try. It's a waste of time. You have to use mutation. Then there's the fact that when you call complete, the one arg you must call the underlying complete. But you also have to take care of not maybe in your complete you have some kind of flush logic, some items that you want to write right now. And you must take care of knowing whether the underlying reducing function is still able to accept new items. Maybe the downstream reducing function has signaled already that it is done and that it can't accept any additional items. So you have to find a way to communicate between the step arity and the complete arity to know when to circumvent some calls. All of this because every time you call the step arity on a reducing function, you may get not a regular value, but a reduced value. And when you write transducer, you never expect to get a reduced. You always forget it. It's so unusual, but you have to keep in mind of always checking whether you are reduced or not. And when reducers were reduced was introduced with reducers, when they were introduced, there were bugs in Clojure core because Wichiki forgot to check for reduced. When transducers were added, there have been bugs in the way reduced value were handled by the transducers. So it's really finicky to get right. So when you've got a reduced value from the underlying stream, from the underlying reducing function, what do you get? What do you do? Do you need to propagate immediately, or maybe you are at a point where the underlying stream just finished, but you are going to finish too. For example, you are implementing something like take. The countdown of take is at 0, so you are going to finish. And so you are going to wrap the accumulator into a reduce to say, hey, take is over. But if you do that without checking whether the underlying accumulator is reduced or not, you are going to end up with a reduce inside another reduced, which is going to break evoke to the caller, which is only going to peel one reduced layer. And it's really a mess. So you better use the ensure reduced and unreduced functions to be sure whether you can to make sure that you have wrapped or that you have correctly unwrapped the accumulator. And in sometimes where you have nested reducing loops, you may want purposefully to return 7 or 8 or whatever deep nested reduced accumulator inside reduced wrappers. It's really not that pleasant. And another place where it's common to forget about reduced value is to forget about them in the completionarity, where you want to flush a value, for example, a window. You have some leftovers value, want to flush them, and you forgot to check that while flushing. And again, it can give you some bad bug. But everything ties together to the fact that the reducing function is a lie. It's a bad API for a transducer. Because the transducer in Clojure is just a mutable process whose protocol should be something like that. Just take a value and finish the computation. It should be only that. But for historical reasons, it had been retrofitted in the reducing function contract, and this is why we've got all these quirks. So if you are going to implement your own transducer, it's all about the quirks are all about implementing your own transducers or transducing context. It's not about using them. But so if you want to implement a transducing context or a transducer, implement with extra care. And like I said earlier, the ternary into model really fits the way I used to program in Clojure. And so I began to use the ternary into a lot. And there was some code that was not easy to express using only transducers. So I started my own collection of transducers, xforms. And xforms works now on Clojure, Clojure script, and even self-hosted Clojure script. So in xforms, you will find a lot of transducers. There are the regular ones, like partition. There's reduction, there's for, there's take class, drop class, window, and window by time. Well, window by time is so-so. I'm really not happy with its API. And then we have the special one. But I'm going to show you first x4. x4 can be used either as a drop-in replacement for regular for, or as a transducer. To use it as a transducer, you just have to replace the first collection in the for binding, vector by a %. And then it returns a transducer. X-partition is really just like partition, but as a transducer, you can provide a step, you can provide padding, but there are some new stuff that partition can do. Partition can also be a transducing context. Here, I pass another transducer, x-reduce plus, to xpartition, to tell xpartition that I don't want to get partitions as vectors. I want to perform a computation over the partitions. I don't want to have a first pass which is going to group things together and then perform a second pass to perform the computation on the groups. So partition expressed like that allows you to perform both computations in one pass. So it's really interesting when you are dealing with a stream of events. For example, I have used that with Kafka. And you can also see that with some transducers, things like join become a simple composition of transducer. Interpose and xstr is equivalent to join. So xpartition is a transducer and a transducer context at the same time. And this pattern of a transducer being also a transducer context can be found in a lot of other transducer functions in xforms. My favorite is byKey, because byKey allows you to perform a computation for a given key, and you provide a key function over the items. And so it becomes very easy to re-implement group by in this fashion. And the fun thing is that this one-liner is about 30% faster than the true group by. And it's really interesting because it's more pluggable than group by, because here you can customize. Instead of returning a vector, you can perform any other computation, maybe another grouping. You can do anything and still you do everything in one pass. And to make byKey very efficient, there's an infrastructure in xform to make it efficient to process key value pairs without allocating pairs. And xn2 is just a drop-in replacement for n2, but which is aware of the pair optimization. And when you provide it only with one argument, it's also a transducer. And so when you combine byKey and nested in a very deep manner, you can express a rollup transducer, which is going to perform a hierarchical aggregation on data in one pass. So this code, which is a bit advanced, when you use it, you specify that you want to roll up this data first by continent, then by country, and then you get this result out. And everything has been computed still in one pass. So very interesting for processing streams of event. And last thing, a promise about transducers is that you can express a computation and port it to different contexts. We have seen the 6 contexts provided by Clojure by default. We have seen that xforms provide its own context in the form of transducers that are both transducers and contexts at the same time. But I've also co-developed a library for Apache Spark, which is named Powderkeg, and which allows you to take a transducer that you have developed at the REPL and tested as a with vectors or whatever, and have it run on RDD on Spark or on streams too. And it's quite easy. It's about 1/3 of the whole API. You call RDD with the source, which may be an RDD or anything which can be converted to an RDD, and then you provide the transducer. And it's going to automatically migrate the code. It runs right at the REPL. You can connect to a cluster without anything special on the cluster. And it's going to push all dynamically generated code at the REPL to the cluster. So you can really live code a Spark cluster using Powderkeg. So to summarize, transducers are really a boon for reusability, and with the added benefit that they are more efficient than the other options. But writing your own transducers is super painful, so try to compose your own transducer from existing ones, because it's really, really painful. And please give xforms or Powderkeg a try. I would be happy to give you a hand. So thank you for listening. You can find me there.
Thank you very much. We do need to get to lunch next, so maybe just one or two questions. Do we have any questions? Okay.
Hi. Oh,
Hi.
sorry, a little loud. I'm the guy developing the sparkling library, and
Yeah.
I heard about Powderkeg right now, and it's mind blowing because you say you don't need to compile stuff on the
IoT.
cluster. Can you elaborate on that a little bit, please?
Yeah, okay. When you start, when you are at the REPL and that you require the Powderkeg namespace, during the installation of the Powderkeg namespace, Powderkeg dynamically generate a Java agent which connects the JVM to itself as an agent to get access to the bytecode of any class. Then it modifies the bytecode of some classes in Clojure Core to be notified about all the changes to all the vars. And then at each time that you need to send something over the wire to the cluster, it emits a barrier. And the barrier is a point where it looks at all the classes that have been defined since the previous barrier, all the vars that have been changed. It serves everything, package into a jar, ship it to the cluster, update the namespaces on the workers, and then evaluate your transformation. For more details about Powderkeg, there was a talk at the Clojure Conch this year.
Okay, one more question.
I've looked at your xform library, and I think the byte is really interesting, but it's also real hard to
get used to.
Yeah, and to understand what it does. Yeah. Under the hood. So do you have a good reference you can point people to? I've looked at the wiki, but still too short for me to understand.
No, it's a bit lacking. You just have to look at the example and try by yourself. But in its simplest form, byte assumes that is getting key value pairs from above. It groups the values by key, as the name says. And then for each key, it creates an independent transducing context. And so each set of value for a key is going to be reduced, transformed by its own transducing context. So if I think still this is one of the simplest examples. Here, it's a bit different because I provide the custom key function. I don't assume key value pairs. I provide a KFN function to extract the key from the value, but it's the same idea. So a value get in, you extract the key from the value using this function. And then you look if you well, by key looks whether there's already a transduction going on for the given key. If there's one, it sends the value to the transduction. And the transduction is this one, accumulate into a vector. So we have already seen the key, then add it to this transduction. In this case, this is add to the vector being built. If the key hasn't been seen yet, it's going to create a new fresh new transducing context for accumulating into a vector and put the value into the vector. So it performs this computation. So creating one transduction for each for each key, and then when the output is exhausted, it closed all the transactions and write the results to the results downstreams, and the results are pairs of the key and the result of the transduction. And that's why they are collected back into a map. So by key, at the end, emits pairs that are collected by int2.
I will have to study that more.
But really, you start by playing with just that and understanding that. You can start by replacing xint2 by, for example, x reduce plus to see that you are going to perform the sum instead of the. And maybe you can also play with short-circuiting it by putting comp take 3, for example. So that is only going to aggregate the 3 items for a given key, 3 first items for a given key. Well, if you want to really get by key, you have to start from there. It's the simplest case.
Thanks.